recording. Okay, there's no camera for me today because I'm sick. Uh, and we're gonna finish chapter 11 today. So chapter 11, from starting from 11.7 all the way to 11.10. Right. So what these chapters are talking about, it's pretty much the strategy that you're gonna use to make things happen that we've seen before. So what we've seen before is pretty much the what, and this second half is pretty much the how. Uh, so let's see what is important here to be read. The mobile state protocol, distributed binding protocol, and the distributed garbage collector. So each language entity is implemented by one or more distributed algorithms. First, the stateful entities. The protocol is related to the stateful entities. We have the stationary state. All operations that always execute on the process where the state resides, calling the target process. Remote invocations send messages to this process. Conceptually, it is as if this was invoking thread moves to the target process. Um, when seen this way, distributed exceptions re-enter locking work correctly. Operations are synchronous. So this is, as far as I remember, this is the case where nobody has access to the thing with a syntax that would be perceived as local. Rather, people have to talk to the owner of the thing, and then the owner does the thing.
Yeah, this is used for ports most notably, because they are asynchronous. So it makes sense that okay, yeah, if you're just sending a message and not waiting for a response, then there's no reason for the ports to move, right?
Yeah. Mobile state. This is the case. In this case, the invoking thread is stationary. The right to update the state moves from one process to another. So this is the one where the is going to be perceived as being done local by whoever wants to do the change.
Yep.
We call this write the state pointer or content edge. An exchange operation will first cause the state pointer to move to the executing process so that the exchange is always local. Well, always perceived as local because there will be a side effect that people will be able to detect. The difference is who is doing the change. If you're doing it yourself, then we're calling that local, but there are some like effect consequences. The mobile state protocol
Yeah.
can be seen as implementing a cache. Yes.
Yeah, this is local in the sense of it's happening on this process, on this machine, not necessarily local in the sense of this is not going to interfere with other computations because, well, it's mutation. The whole point is that it does interfere with other computations, right?
Not only that, but we this allows you to have a more like it's more uniform because now you have the same syntax to do changes that are actually local and that you can also use to do changes that are perceived as local but they aren't. So this creates some sort of uniformity, and I think that's nice. I just think it may be confusing for newcomers to the project because if you have a function, just by reading the function itself, you may not be able to initially detect that this is doing something more than just locally updating a variable. But you will eventually be able to tell because you're going to have to find a ticket being used somewhere, right? So even though the syntax will be perceived as being local, when you see a ticket or a function that interacts with the ticket mechanism, then you're going to be able to tell.
Yeah,
Yeah, in the
basically.
case of Karuta, you're going to be able to tell immediately because the predicates that are actually coming from somewhere else have a syntactical difference. So it's kind of like a middle ground. It's not the same syntax as it would be if it was local, but it is similar enough so it's not very intrusive. And then invalidation, which is what Marinho explained to me last time. I still have the same criticism. This difference between writing and reading should be have said before, not here, because I think it makes the previous reading more confusing, the absence of this there. But the protocol optimizes the mobile state protocol when reading is much more frequent and updating. A process that wants to read the state sends a message to the target process and gets the state in reply, thus creating a local replica of the state. A process that wants to update the state must first explicitly invalidate all these replicas by sending them an invalidation message. This guarantees that the interleaving semantics of the state updates is maintained. the right to update the state still moves from one process to another. Very okay. Now, this was already foreshadowed by Marin. Single assignment
Yep.
entities are implemented with a distributed unification algorithm. The key operation of this algorithm is a distributed bind operation, which replaces the variable by whatever it is bound to on the process that know the variable. So there are two variants, the lazy binding and the eager binding. The lazy binding, which obviously is understood as by demand, the replacement is done in a process only when the process needs the variable. This variant reduces the number of network messages but increases latency and keeps a dependency on a variable's home process. How is this increasing the latency? That's kind of my question. The first part
Be,
of it, which is
be,
reduction of the number of network messages, makes complete sense. The other one, I don't really get it.
because because if you're going with the eager strategy, which is what Mozart uses, as soon as somebody somewhere binds a variable that you have a reference to, they will send you a message saying, "Hey, this is bound now." Um, but if you're doing lazy binding instead, what's gonna happen is nobody's gonna send you a message. But then you're gonna be like, okay, I need the value of this thing. Does is this bound already? Then you have to wait for a reply. You see?
Ah, okay, so you're counting as the extra latency, the waiting after you demand it. I see.
Yeah, yeah,
Yeah, and then we have the eager binding, which is updating people as soon as possible about the bind. Stateless entities are implemented with one of the two or the following three protocols. Yeah. So lazy copying, the value is copied to a process when the process needs it. This reduces the number of network messages, but increases latency and keeps the dependency on the original process. Just a reminder, stateless entities are being shared by writing to a file. So all of these strategies are regards when are you gonna have your version, like somebody updated the file, when are you gonna get the update? This is what we're talking about. Then the lazy copying, you're only gonna get the update as soon as you need it, which probably also has the same latency problem for because of the same reason that Marin just explained. Eager copying. The value is not sent as part of the message, but if upon reception of the message the value is not present, then an immediate request is made for it.
yeah. This is the as we will see in the table on the next page. This is just for functions and functors and procedures and things that have code inside of them generally, right? Um,
Mhm. So if you
and
receive
you
a
can do
message
this,
that references them, you immediately request for it.
yeah, and you can do this because they have a unique they have a unique identity. So like, if you keep track of that when you send and receive messages, you can see that, oh, okay, I saw this identity before, I have the code already, so I don't need to request it. But if it's the first time you're seeing it, then you'll be like, okay, I don't have this, give me the code. And that requires an extra round trip, but it's only the first time that you see that particular entity, right?
Yeah. In most cases, the wait. Could you repeat the last sentence, Marin, just for me to see if I got it?
Yeah, this requires, if it's the first time that you receive an entity like a class or a functor or a
Mhm.
procedure,
Mhm.
something that has
Mhm.
code inside of it, um, if it's the first time you're receiving it, you need an extra round trip because you need to say, hey,
Yeah.
you gave me this
Yeah.
thing,
The
I never
upfront
saw
cost
it
is higher.
before, give me the code. Sorry?
The upfront cost is higher.
Yes, but the overall cost along the runtime of the program is lower
Of course,
because
yeah.
you don't have to keep copying it everywhere.
Exactly. Yeah, no, completely agree with that. In most cases, this is an optimal protocol since the value will be present in the receiving process for all except the first message referencing it. Eager immediate copying. The value is sent as part of the message. This has minimum latency, but can overload the network since values will be repeatedly sent to the processes. It is used to send record structures. This also has the drawback of the payload being larger, because if you have a dependency chain of like a function that uses another function that requires a functor that uses a class, then all of those things need to go. So,
Those those wouldn't use this protocol, but yeah, if you have a record that has another record that has another record that has a big table with like 10,000 things in it, then yeah, the message will be large.
Yeah, if you are doing something like that, you're probably going to be using the lazy version because of obvious reasons, but nothing forbids you from using this version. Um, and then in addition to these algorithms, there is a distributed garbage collection algorithm. This algorithm works alongside the local one. The algorithm does no global operations and is able to remove all garbage except for cross-process cycle between stateful entities. The algorithm consists of two parts, a credit mechanism and a time lease mechanism. The credit mechanism works well when there are no failures. It is a kind of weighted reference counting. We're going to see more about that later. Each language entity with remote references has a supply of credits. Each remote reference to the entity must have at least one credit. When a local garbage collection reclaims a remote reference, then its credits are sent back. So the local garbage collector has some sort of communication with the distributed one. And then when the local reclaims a reference that is actually remote, then we need to do something about the credits. When an entity has no outstanding remote credits or no local references, then it can be reclaimed. So the credits is essentially a way that we can tell if anybody else needs it, and then we can use the local mechanism to tell if we need it. So that's pretty clever.
Yeah, and by using both together, you can figure out if anyone needs it.
In the time lease mechanism, each distributed entity exists for a limited time unless it is periodically renewed by a message sent from a remote reference. I found that this time lease mechanism is kind of more like, it sounds like more complication. I understand the benefit that you are more, potentially more in a more optimal way getting rid of the garbage. But at the same time, you need to keep sending those messages that essentially may be useless and be putting more burden on the network just for the sake of saying, hey, actually, I need this for 3 days, but I need to keep sending you messages because.
I mean, maybe there's a way to choose how long the lease is gonna last, and then you can say, okay, I need this for 3 days, and then you only need to send another message 3 days later if you need it longer.
Sure.
Um, but the point is that they just should figure out if the network has troubles and prevent you from holding on to garbage that nobody else is actually referencing.
Yeah, and in a particular way is also faster, right? Because with the other one, you need to, for the you need you have the burden of the local garbage collector and the credit system. The time lease mechanism sounds simpler on the implementation perspective, and that's probably one of the reasons that this is an option. It's because it's simpler, but it has this drawback of like, okay, but this needs to be customizable AF in order to be actually like general.
I mean, that's what you're getting into when as soon as you do distributed computing, so it checks out, I guess.
Yes, Table 11.1 shows the algorithms used by the current system for each language entity. In this table, an object consists of two parts, the object record and the object state. We conclude that network operations are predictable for all language entities, which gives the programmer the ability to manage network communications. So there is this table, which essentially is a way, like this is a cheat sheet, so you can use this when you are implementing a distributed thing. You see the kind of entity you're interacting with, and then you pick one of the options available in this cell. And then you have to think about it. What is your domain? What is your requirement? What are your requirements? Things like that in order to properly evaluate. So if you are in a situation that we said before, that you have records within records within records and class and stay a bunch of like nested stateless entities, you probably should not use particularly the eager immediate copying. And then you have to think about things like that. That really depends on whatever you're doing. Um, Mobile state protocol. Yeah, so this is pretty cool. Well, it has caveats, as I'm gonna mention to Marinho to see his opinion, but this is pretty cool regardless. Um, we use a graph notation to describe the protocol. So just for a reminder, what is the mobile state one? It's the one is the one used to implement stateful state entities. Okay. So object cells and logs are implemented with this one. We use a graph notation to describe the protocol. Each language entity or record procedure validated for variable, thread, and cell is represented by a node in the graph. To represent a distributed computation, we add two additional nodes called proxy and manager. So the proxy is essentially potentially another thread that you're gonna interact as your like personal manager, and then the personal managers talk to the big manager, and then the big manager does the coordination. And I would bet that there are different strategies and topologies that you can use on top of this. Because right now, this has a gigantic problem, which is what happens if this guy dies? We're screwed.
Yeah, you probably need some kind of heartbeat system to say, okay,
And
that
lifting as well.
yeah, then you can say, okay, the process that holds the manager to this thing died. We probably need some kind of consensus to figure out who should be the manager now that the original one
Exactly.
is no longer available.
Exactly. Um, yeah, each language entity has a remote reference has remote references represented by a star-like structure with one manager and a set of proxies. Yep, that checks out. The proxy is the local reference of a remote entity. The manager coordinates protocol that implements the distribution behavior of the entity. The manager is also called the coordinator. Yeah, of course. Manager. Yeah, so again, even though it stands for proxy, I prefer personal manager. That works. One moment. Okay, I'm back. Uh, cool. Figure 11.6 shows a cell that has remote references on three processes. The cell consists of three proxies P and one manager M. The cell content X is accessible from the first proxy through the state pointer. So we're talking about
Mm.
this X here. Okay?
Actually, there's one situation where it's actually impossible to recover. What happens if the process that codes the state pointer dies?
I think you're done.
Yeah, like there's nothing you can do at that point, right? Because the current state is lost.
Well, actually, I lied. This is gonna be expensive, but there is a way around that. You could have um, some sort of backup, like secondary personal managers that hold a table with state pointers that matter, and then they serve as a cache because if we lost it, we can do a lookup. So you can add a level of redundancy on top of it. That is very expensive because you're potentially not going to need that and you're wasting resources doing that, both in terms of time and memory. But that could be in a very critical system, like, I don't know, a satellite going to space or things like that. You could use that as a redundancy layer. But yeah, so on this particular case here, if you lose the process that has the state pointer, you're done. There's really nothing you can do about it. Do you agree, Marie?
I agree.
Okay, so a thread T on the third process references the cell, which means that it references the third proxy. A thread T on the third process references the cell. Yeah, yeah. What happens when T does an exchange operation? The state pointer is on a different process from T, right? Because we want to do it in here, these X here. Yeah. So the mobile state protocol is initiated to bring the state pointers to T's process. Once the state pointer is local to T, then the exchange is performed. This implies the remarkable property that all sales operations are always performed locally in the thread that initiates them. Yeah, of course, because this is not the stationary version, right? So we are actually going to exchange the ownership of this to whoever wants to do the operation. So you have to do that. So what does that happen, right? So the guy that wants to do the thing does a get to the manager, the coordinator manager, and then the coordinator manager goes to the proxy that actually owns the thing currently, and actually that this the owner talks to the requester directly via a put, and then this can do the thing. It's not specified here, but what happens when the requester is done? Are we gonna just like this guy is the new
It,
owner, or is gonna pass the baton back?
it's gonna stay there until somebody else takes ownership of the state pointer.
Okay. Okay, so that figure explains that. The third proxy initiates the move by sending a GET request to M. The manager M plays the role of a serializer. All requests pass through it after receiving the GET. Yeah, I have a question, actually.
Okay.
If we are already doing a direct put from the owner to the requester, oh no, I think I answered myself. I was about to ask why we need the middle guy. But the answer is because you may not know, because this is a new process that joined the network dynamically, but everybody knows the central one. So I may not know, like this guy may not know the owner and vice versa, but if we have somebody that we both know, then we can do the exchange. And we can identify ourselves so we can do the put later. Okay, that makes sense. Uh, Okay, so then manager M plays the role of a serializer, blah, blah. After receiving the get, M sends a forward message to the first proxy. When the first proxy receives the forward, it sends a put to the third, and then this atomically transfer the state pointer, blah, blah, blah. And now the binding version of this. So this is used for the bind of a dataflow variable, which is going to be a distributed unification process. When unification is made, distributed, it turns out that the whole algorithm remains centralized except for one operation, namely binding a variable. Let's give intuition about it. So figure 11.8 shows a dataflow variable v that has remote references on three processes. That is a lie. There's no v in here. But, well, it's going to make sense later. Like the distributed cell, there are three proxies P and one manager M. Yep, that checks out. Um, The manager has references to all proxies. Again, that's the main reason we need a middle guy, is because everybody has access to it. On the first process, thread T1 references V, and it is suspended on this operation. So thread 1 is the one on the left. On the third process, or the one on the right, there's also a thread T that references V and is about to do the binding, right? So this is very important because the guy on the right is essentially binding something that the guy on the left is blocked by. So that's the reason that matters. The protocol to bind V consists of two messages, request and binding, and then we have this other diagram here. Um, so you do the request as saying, hey, I bound this, and then it does a
Yeah, the
broadcast this
manager does
information
a
for everybody
broadcast.
else. And why is this important? Because maybe why do we have to do this binding? Because maybe somebody already or else already did that, and you should be informed that this is a failure.
Yep.
So that's why we have to go back and forth between the guy on the right and the manager. It's because you need to inform that yes, you can do that. Um, you can actually do that. Probably for the sake of simplicity, this could just be an acknowledge, like ACK, and if you have an error, then it's something else. But just to be simple, an acknowledge message there. The third process initiates a protocol by sending request 10 to M. The first such request received by M causes a binding to send to all proxies. This action is at the heart of the algorithm. The rest is details. If M is already bound when it receives a request, then it simply ignores the request. This is correct since the proxy that sent the request receives a binding in due course. Actually, that's true. Why do we need to do this then?
It's what you said earlier, right? You need to
Well,
be
but
able to know.
they refute it because they just said that if somebody else before you did that, you would already have received the binding from the other guy that did it
Ah,
earlier.
but you're not considering the network delays, Lemos. It could be the case that you send the request while there's a binding coming your way that hasn't arrived yet.
Oh, okay. So you're saying that there may be a racing condition that will only resolve during the network travel, right?
Yeah.
Oh, okay. No, then it's what I said earlier. If a new proxy is created, yeah, this is correct. Well, but if a new proxy is created on a fourth process, then it must register itself with the manager. There are a few more such cases. They are all explained there. This algorithm has several good properties. In the common case where the variable is on just two processes, for example, where the binding is used to return the result of a computation, the argument's latency is a single round trip. This is the same on explicit message passing. A binding conflict will cause an exception to be raised on the process that is responsible for the conflict. Um, well, not really. Well, actually, really, but this kind of has the caveat that maybe you actually requested the binding first, but because of the round trips and the available nodes until we reaches the manager, maybe the second guy will reach first because there's less hops between the second and the manager, and then you're gonna say that's kind of like a situation, right?
I mean, that's similar to the local case where you could have two threads trying to bind the same variable to different values, right?
No, yes, but in differently than the threads that is happening on a single computer, the network may put the first one into a disadvantage because of reasons that it doesn't have control over.
Well, the same is true of the local case though, because you don't really have much control over the scheduler. What happens if the second thread, the one that did the binds later, is actually a higher priority
Yeah,
thread?
but at least the scheduler is trying to be fair. In here, it's not about fairness, it's about how many hops and how many computers you have along the way. That's completely different. You don't have control over any of that because maybe, I don't know, that region has more computers because there are more users that use the service. That's fair, but that's not trying to be fair. The scheduler at least is trying to be fair. So I would say that even though you may encounter the same situation locally, you can at least try to tweak a little bit the fairness. In here, what are you gonna do? Put more empty buildings with computers just for the sake of having, of like what are you doing, you know? Memory management. When distribution is taken into account, the Mozart system has three levels of garbage collection. A local garbage collector per process. This collector coordinates its work with the distributed collectors. A distributed garbage collector that uses weighted and reference counting. And a distributed garbage collector based on a time lease mechanism. Okay, so the first one, this is just the local one. We haven't gone through the details of that, but this can just be the same classic algorithm of detecting dead references. And then we're going to see these two. Weighted reference counting. The first level of distributed garbage collection uses that. This collector works when there are no failures. It can rapidly remove all distributed garbage except for cross-process cycles between stateful entities on different owner processes. Each remote reference has a non-zero amount of credit that implies the continued aliveness of the entity. When the remote reference is reclaimed, the credit is returned to the owner. When the owner sees that there is no longer any outstanding credit, then the entity can be reclaimed if there are no more local references. But this is kind of interesting. It's not that the wallet is zeroed. It's more no longer outstanding. So there is a threshold, and if it's below the threshold, you're gonna kill it, even though there are still people using it.
That's not quite it. It's more like you generate a credit for each external reference that is in another process but points to you.
Exactly.
And then as those processes finish doing their business, they will let you know, hey, I'm no longer using this, and then I'm returning your credit. Here you go. Um, When there are no more credits that you are waiting to be returned, that is, when the reference count is zero, then you can defer to the local garbage collector in that case.
But that's not written in here. At first, I thought exactly what you said. But now that I'm reading for the second time, this is not saying what you said. Or do you disagree?
I disagree, actually.
Okay, so you read when the owner sees that there is no longer any outstanding credit, you read this as being zero.
Well, yes.
I cannot agree with that. This definitely doesn't say anything about that. But okay. Weighted reference counting is efficient and scalable. First, creating a new remote reference requires essentially zero network messages in addition to the message sent by the application. Um, yeah. Second, each remote process does not need to know any other process except the owner process, which is good. Third, the owner process does not need to know any remote process. Yeah, the second is good, but there is a caveat of like, if the owner dies, everybody's screwed. Timeless mechanism. The second level uses time. This collector works when there are permanent or long-lived temporary failures. Each remote reference has only a limited lifetime and must periodically send a lease renewal message to the owner process. If the owner process does not receive any lease renewal messages after a given long time period, then it assumes that the reference may be considered dead. The time release mechanism is complementary to weighted reference counting. The latter reclaims garbage rapidly in a case where there are no failures. The former is much slower, but it is guaranteed infinite time to reclaim all garbage because of failure. This plugs the memory leaks to failure. Well, the former doesn't necessarily need to be slower. You can put a very tiny delta, but
But then you
as
are
you start
less
having
tolerant of network oscillations if you do that.
exactly. The trade-off is that if the going through the network starts to take a little bit more time because you are expanding your product, you are expanding your program, and making it like other in other places, then the latency starts to matter, and then you need to increase the delta if you like if you want to be more tolerant, as Marinho just said. Programmer responsibility. The main problem with distributed garbage collection is to collect cycles of data that exist on several processes and that contain stateful entities. As far as we know, there does not exist an efficient and simple distributed garbage collector that can collect these cycles. Yeah, so
Well,
what is this saying? Go on.
it's basically the same problem of any reference counting system, except there's the complication that the two references are not even on the same machine anymore.
Exactly. Uh, this means that distributed memory management is not completely automated. The application has to do a little bit of work. For example, consider a client-server application. Each client has a reference to the server. Often, the server has reference to the client's discrete cycles. If the client and server are on different processes, they cannot be reclaimed. To reclaim a client or a server, it is necessary to break the cycle. This has to be done by the application, which means that you're going to have potentially lines of code that will make no sense from a perspective of solving the problem, but they are there because they need to break the cycle that is like transparent if you don't know about it beforehand. So that kind of sucks because that puts you in a situation where you may have a lot of code that it's going to be like exposed, and it's not a good thing because people may ask, what is this doing? What is this for? Is this helping us solving the problem? And the answer will be no, but we need this in order to break cycles and help the garbage collector. One way to get around that is to actually use some sort of abstraction to put that under the hood from the day-to-day programming, such as a macro. So you make a macro that allows you to write simple stuff and automatically somehow does the quote unquote nonsensical code, and then nobody's gonna care. That's one
It
way.
doesn't even need to be a macro, it could just be a procedure. The other alternative is to just say, okay, we're not going to do distribution because it's too complicated. I wish more people took that option.
Before I go into that, I don't think it can be a procedure because that won't have the nice syntax for day-to-day programming. Because I do want to give you like a def n, so you actually think you are actually implementing a function, and you are, but under the hood there's some unnecessary, from the application's perspective, necessary things to have to be done for technicalities. So that's why I thought of a macro. But if you are okay with having to like extra syntax, you can use a procedure for sure. I just wanted to make it more convenient. And about the second comment, which is about just don't do distributed, is like, man, you can't solve problems by doing that all the time. Some problems require you
Mm,
to do that.
well, some problems do, but not all of them. Certainly not as many as people think.
I think, but I
In
think
case
there.
you didn't notice, this is about microservices, Lemos.
No, yes, sure. But for example, if you're making a game, if you're making like distributed Lyceum implementation, you must be distributed not because like we wanted to do microservices, but because there is a latency problem in an MMO that matters.
Well, in that case, the problem that you're trying to solve is intrinsically distributed. So in that case, yeah, you can't run away from it.
Yeah, but I agree that making it distributed for the sake of it is a bad idea. You need to have a very clear argument, objective argument, that justifies going out to all these problems. And that is only talking about, like, we're not even talking about all of the problems that this puts you. Because, for example, if you have a distributed system, and how are you going to manage the data? Because all of these problems are problems on the application language level. So we are trying to make distributed OS. What about the data that you're storing with potentially another technology? So there is also that problem. So it piles up. So you should have a very good reason. Um, okay, so to reclaim a client or a server, it's necessary to break the cycle. This has to be done by the application. There are two ways to do it. Either the server has to remove the client reference or the way around. Creating a ticket makes X a permanent reference when using offer unlimited. That is, X is added to the root set and is never reclaimed. Once only tickets, such as the one using offer, can only be taken once. As soon as they are taken, X is no longer a permanent reference and it potentially reclaimable again. It is possible to use distribution to reduce the time needed by local garbage collection. With remote, create a small process that runs the time critical part of the application. Since the process is small, local garbage collection in it will be very fast. Yeah, very crazy that this language allows you to do such a thing. It has a little bit of a Lisp vibes. Like everything is open, you can call all of it yourself.
Yeah, it also has a little bit of Beam vibes because, well,
Yeah,
the
of
Beam
course.
also is very, very open as well.
Yeah. Partial failure. So let us now extend the distribution model with support for partial failure. We first explain the kinds of failures we detect and how we detect them. Then we show some simple ways to use this detection in applications to handle partial failure. So fault model. The fault model defines the kinds of failures that can occur in a system. Um, we have designed a simple fault model that captures the most common kinds of failures on the internet. The most resistant can detect two kinds of failures. So we have permanent, and permanent process failure is commonly known as a fail silent with failure detection. It is indicated by the failure mode perm fail. A process stops working instantaneously, does not communicate with other processes from that point onwards, and the stop can be detected from the outside. Permanent process failures cannot in general be detected on a WAN, but only on a LAN. Yeah, if somebody on the internet exploded, how are you gonna know that that was the reason? It is easier to do that in a local setting.
Yeah,
Network,
there's always the chance that the cables were just cut and they would take like a day to be repaired. But in the meantime, you have no idea, right?
yeah, exactly. Network inactivity is a kind of temporary failure. It can be either temporary or permanent, but even when it's supposedly permanent, one could imagine the network being repaired. It is different from process failure because the network does not store any state. Network inactivity is indicated by the failure mode temp fail. Yeah, so this is really important because if somebody dies and they were holding things that the other people were taking for granted, then that's a different problem than like somebody went through the wire and like it's turned off the modem, right? That's not the same thing as like an exception exploded and it's permanent and that caused some issues and somebody cut the wire. It's not only like unplug it but like cut it. So that's more permanent than this one. Uh, and then the reflect. How do those reflect in the language? Synchronous and asynchronous. The synchronous detection is done when attempting to do an operation on a language entity. If the entity is affected by a failure, then the operation is replaced by another, which is predefined by the program. For example, the operation can be replaced by a raised exception. Asynchronous detection is done independent of any operations. A program first posts a watcher on the entity before any problems occur. Later, if the system detects a problem, then it enables the watcher, which executes a predefined operation in a new thread. Users use the well-known heartbeat system for failure detection. Um, yeah, even though they are classified as synchronous and asynchronous, I think they are pretty similar in the sense that you have to have a predefined something to take care of it. On the synchronous case, you have to have a predefined program, and in the asynchronous case, you have to have a predefined operation on a new thread. So they have that similarity. The
Uh,
reason it needs a watcher is because the program went through, like it's asynchronous, it didn't get blocked. So you cannot immediately, after timing out, you can immediately call the predefined program. You need to inspect another entity to be able to tell that somebody went wrong because it's asynchronous.
yeah.
The true failure modes detected either both ways are sufficient for writing fault-tolerant to disputed applications, and there is a module for that called fault. So first of all, the network inactivity. So this is the classic timeout. The default behavior of TCP is to give a timeout after some minutes. And then we're going to use a temp fail exception for that. The purpose of temp fail is to inform the application of network problems, not to mark the end of a connection. For example, if the application is connected to a server and if there are problems with the server, then the application would like to be informed quickly so it can try reconnecting to another one. Attempt fail failure mode can therefore be relatively frequent, much more frequent than a timeout. In most cases, attempt fail fault state will eventually go away. Well, that's why it's called temporary.
Yeah.
But it's possible that lasts forever. Um, if a user disconnects the network connection of a laptop, then only he or she knows whether the problem is permanent. The application cannot in general know this. This decision whether to continue waiting or to stop the wait can cut through all levels of abstraction to appear at the top level. The application might then pop up a window to ask the user whether to continue waiting or not. The important thing is that the network layer does not make this decision. The application is completely free to decide or to let the user decide. Yeah, letting the user decide is not a good idea in general.
Sometimes it is the right thing to do, though.
Well, but there are very few cases where we can properly inform what the heck is going on. So, for example, everybody, I assume, already suffer from the problem that a tab is taking too long to load, and then a pop-up comes in asking, "Hey, do you want to wait this or do you want to close it?" That's fair, but not all problems can be solved by asking that question, because maybe waiting more or waiting less has consequences. Are you gonna
The
list all of those to the user?
No, 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 no. The point is not that you're always going to ask the user. The point is that the application can decide what to do, and that includes maybe asking the user.
Yeah, no, I'm okay with the freedom. I'm just saying that you should do something else aside. You should consider doing something else aside from asking, because not every time you're gonna be able to do that. And then, okay, Unix. We have problems about that. I was about to say Unix, but I guess this is more general. A surprisingly large number of existing systems incorrectly handle prolonged network inactivity, and then they just abort with a timeout, and that actually sucks. SSH is a very common example of this. The mistake in this approach is that the decision to timeout is made at a wrong level. For example, assume that there is a timeout in the lower layer and the transport layer of the network interface. The timeout crosses all abstraction boundaries to appear directly at the top level to the user. If the user is informed in some way, the application stops and at best a window is open asking confirmation to abort the application. Yeah, this is the example that I just said. The user does not have the possibility to communicate back to the timeout layer. This limits the flexibility. Yeah, this is essentially doing a bubbling up operation that is not required at all.
And worse, it's a bubbling up that's only one way. You can't talk back to the layer where the problem originated, right?
No, yeah, but
Necessarily.
yeah, but then it's a two-facet problem. First, it should not bubble up immediately. You should have done as a programmer be able to catch it on the application layer or anything on top of it and do something about it. Or if you are allowing it to go through, you need to be able to go back, as you just said. So it's two problems now. The right approach is not to time out by default, but to let the application decide. The application may decide to wait indefinitely, or to abort immediately without waiting, or let the user decide. This greatly increases the perceived quality of the system. And then there's examples. Cool. Simple cases of failure handling. Okay, so this is now a little bit of code on how to do that. And we're going to use the fault module. So disconnected operation. So you imagine that you are doing a dial-up connection. This is very old. Nobody does that.
I mean, this is a book from 2003, right? So,
I think that was, I don't know, man. I have a hard time believing that people were still using that frequently at that time.
some people were. That was the very tail end of the dial-up era, but yes, there were still dial-up connections at that point in time.
Um, you might want to hang up to make an urgent phone call, or you are connected to in an airport and your calling card runs out of cash. The phone company just drops your connection unexpectedly. You would like our application to be impervious to this kind of fickleness. That is, you would like the application to wait patiently until you reconnect and then continue working as if nothing went wrong. Man, that would be so awesome because you are in the airport and you're doing some work, and you need to keep in mind that as soon as you join, like as soon as the plane is taking off, you need to remember to do a commit or to save your stuff that requires a constant internet connection. If this was the case here, we could just make the program block until the reconnection was regained when you like arrive at your destination. It would completely change the quality of life of doing programming on the fly.
Literally on the fly, you mean?
Yeah, not only metaphorically, but also literally. In Mozart, this can be achieved by setting the default failure detection to detect only permanent process failures. So this is how you do that. I don't know where this is gonna live. Probably in like a boot up, yeah, startup. This means that operations will only raise exceptions on permanent process failures. On network inactivity, they will wait indefinitely until the network problem goes away. Detecting a problem and taking an action. Yeah, I never suffer from this. On many computers, booting up is an infuriating experience. How many times have you turned on a laptop only to wait several minutes because the operation system expects a network connection and has timed out before going on? Oh, so this is talking about Windows specifically. Probably. Because
Shots
Windows is the
fired.
only operating system that I'm aware that I remember like taking a while because it was trying to do some sort of internet connection beforehand. I'm not I haven't used Windows since 2022, so I'm actually not sure how the situation is over there.
I left Windows even earlier than that, so yeah, I have no idea.
Mozart cannot fix your operating system, but it can make sure that your application will not have the same brainless behavior.
Yeah, shots fired. Shots fired.
Yeah. Assume you want to reuse a remote port. If the remote port has problems, then the application should be informed of this fact. So this is essentially installing a procedure, which is the watcher for this case of the temp fail. The procedure passed to install watcher is called a watcher. It will be called on its own thread as soon as the system detects a problem. It's up to you to do what's necessary. Set an internal flag to indicate that no communication will be done. If the problem was temp fail, then it is possible that communication with X will be restored. If that happens, Mozart allows you to continue using X as if nothing wrong had happened. But it should block, probably. It will block.
Well, you could block. You could set a flag or something to abort but try again later. There are options, right?
I'm a
But
little bit
blocking is the easiest one, I think.
I'm a little bit confused. Is this watcher working for both kinds?
This one is actually.
That's wrong. You should not do that, but cool.
Well, this is just an example, and the only thing it's doing is printing a message.
This is an
So,
example of a bad practice. So that's my counter.
well, this is an example of how you can capture the failure. It doesn't show you how you would handle it because that's up to the application that you're writing, right?
But you could do the same thing for two separate watchers for two separate things. Just to not like because I don't see a reason why would you not just put okay, just do two watchers. Like is this laziness? I thought I was the Haskell guy.
Well, each watcher lives in its own thread. Maybe you don't want separate threads.
Ah, okay. Yeah, but there should be a footnote somewhere saying don't do that. Anyway. But that's okay. But the thread argument is a little bit more understanding. Resilient server. The new stat operation for creating stationary objects. Blah blah blah. Attempting to perform an operation on an entity that requires coordination with a remote failed process will raise an exception. We have to do something about that. We're going to use a try catch for that, and it's going to look like this at the end. The only difference, as far as I can tell, is that there are try catches in the for loop and in the send as well. So
Yeah,
there's
that's
that.
pretty much that's pretty much the difference.
Since the statement X exception also binds X, we protect the client. Boom. Um, in general, any operation on a distributed entity has to be wrapped in a try. The complete definition, blah blah blah. And then note that the distribution faults shows up as exceptions of this form. Okay. If temp fail is enabled, the stationary server defined here will be slowed down if there are communication problems with the client. It will wait until temp fail is raised. One way around this problem is to provide multiple. They didn't fix that. It's still wrong.
Well, there is a different way to fix that, which is to make the server multi-threaded, right?
No, 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 no. I'm talking about this typo here.
Oh, the lack of the letter L. Okay.
Yeah, they didn't fix that.
Oh, that's still in the
That's
new
still.
version of the book
Yeah,
that you have?
yeah.
Okay.
Is to provide multiple server objects to allow serving multiple clients simultaneously. Yeah, this is because you're gonna block the server until you receive the temp fail, right?
Yeah.
Yeah, that makes sense. Active fault tolerance. Applications sometimes need active fault tolerance. Part of the application is replicated on several processes, and our replication algorithm is used to keep the parts coherent with each other. Building entities to provide it. This is an active research topic. They use in Mozart a replicated transactional object store called global store. This keeps copies of a set of objects on the several processes and gives them access to them through a transactional protocol. The copies are kept coherent through the protocol. As long as at least one process is alive, the global store will survive. Yeah, so this is kind of
Uh,
what
it's
I
kind of
said.
like it's kind of like Minigia as well, right?
It's kind of like amnesia, but this is kind of what I said about, okay, how do we fix the problem if one of the proxies die?
Oh, there you go. They actually have a solution.
Yeah, this kind of also, well, but that's a separate, those are separate levels of abstraction, but the same idea could be applied for both, because one of them is on the level of processes. The other one would be on the level of proxies. So that's not the same thing, and that may implicate in different scenarios and problems to solve, but this could be used to solve that as well. Because of the failure detection provided by the fault module, the Mozart system lets the global store and other fault-tolerant entities be written completely in Oz without recompiling the system. Ongoing research, blah, blah, blah. So this is essentially a caching system. So you can be, yeah, you can be fault tolerant if processes die. But it sounds expensive.
I mean, if you assume that each process has a full replica, that is expensive, yeah.
An application is secure if it can continue to fulfill its specification despite malicious failures of its components. Security is a global problem. A weakness in any part of the system can potentially be exploited. Yeah, and then, man, this is so would be even like this is very short section. Yeah, it's already done. But this would be way harder if they mentioned quantum computing or something. But I guess at the time it wouldn't make sense to talk about that
Uh, I
because
mean, there are.
there is a premise here that people are considering to be broken after that becomes a thing.
I mean, there are ways to do encryption and hashing that are resistant to quantum
Yeah, yeah,
attempts
yeah.
to break it.
It's not like people are observing the potentially like complete catastrophic downfall of all the security in the planet. They are already thinking of algorithms that will counter the power of quantum computing. But it is true that if until all of those algorithms are implemented everywhere, there can, especially in legacy systems, quantum computing has a dangerous power, right? Imagine, do you think that after that they make encryption for quantum, I don't know, our government will use it immediately? Do you think that? Do you think that?
They would be entirely too competent if they did that, so no, they won't.
Exactly. So that's the problem. Legacy systems that are potentially still using PHP and COBOL, if they are using that, imagine which type of encryption they are using.
They're they're probably using something like MD5 for hashing or something, right?
Yeah, exactly. So the premise that you can make something so expensive as far as to not make it cost effective for the attacker, that premise will fall, at least temporarily, in legacy systems. Um, and that would make this section way spicier. But let's see what you can do about it, because there are the levels, the layers, the onion. So first, the outer layer of the onion, the application security. This is a property of the application program. The application can continue to fulfill its specification despite the adversaries whose attacks language within the permitted operations in the application itself. So this would be, I don't know, the JavaScript of the website, things
Yeah,
like
that's
that.
one example. Not only the JavaScript, but also all of the communication with the backend and how you can access
Yeah,
the backend resources through the browser and all
yeah.
that. All of that is application layer.
Language security. So this is about the security of the host language itself, in this case JavaScript potentially. You may know that if you do an overflow, something crazy happens, and then you can exploit that. Um,
Yeah, and this may be different for a different part of your system, right?
exactly,
If it's written
exactly.
in multiple languages.
And it's not written in here because that would be kind of controversial, but you can also exploit the ignorance of the people using the language. So, for example, row level security, right? So in Postgres, there is a thing called row level security, It's not talked as much as I see people talking about it, and it's kind of classified as a niche thing, even though it makes no sense to be niche. But if nobody's using it, you can essentially remove that variable from the equation if you want to attack it. So
Yeah,
yeah,
that's a failure of security at the application layer potentially. It's
yeah.
like the language gives you this primitive, but you're not using it, so yeah, screw
Not
you.
even no, it's not about using it. I'm talking about even a worse problem, which is awareness. Um, okay.
Well,
Implementation. Yeah,
there's
go on.
there, there's a solution for that. You can go read the freaking manual.
Yeah, in the case of Postgres, you're gonna suffer a little bit because it's enormous, but it's your job as a DBA to do that. You have to try at least. That's kind of your job. That's what you're being paid for. It's not an excuse to say, oh, nobody uses row level security. It's not an excuse to say this is not very well uh, shared among the community. Yeah, if you're using a tool, you need to know you need to try your best to know more about it. So that falls on you. Even though this point is kind of saying that there is a problem, that it's as a property of the language. I'm talking about something that is kind of like more behavioral, in the sense of the user of the language is a problem. Um,
Uh,
yeah,
yeah, I think a good example of language security would be languages that have automatic memory management, where you don't have access to raw pointers, right?
yeah, but that
There's
goes
a
to that goes to this problem.
Well, yes, if you assume that the implementation is correct, then the not having raw pointer manipulation is a security feature, but then you have to assume the implementation is correct, which it may not be.
Exactly. So this is talking about like in a secure language, applications can continue to fulfill, blah blah blah. So like the language needs to be good, but the implementation of such specification also must be good. So this is talking about, okay, is there a problem in the runtime? We faced this when we did Chime. We discovered a runtime error in Objective-C. Like objectively a problem. It was not like, oh, this is a problem. No, 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 no. We made a program that was having its semantics changed because of where the printf was. That is a like textbook definition of a runtime problem. So that's
Yeah.
implementation security. Operating system security, network, and hardware security. And then this is essentially the core. Like this is the outer layer, then goes to this layer, and this is essentially the heart of the onion, which are the hardest ones to fix because you may have like like this is definitely the easiest one. On an operating system, good luck. You're gonna have to write that yourself because there's only essentially three options in the planet.
Which
And
are?
Windows, Mac OS, and Linux flavors.
I mean, you could always use Gnode or cubes.
Yeah, no, yeah, that's true. There's also some autistic niches, such as cubes. The system is secure if applications can continue to fulfill the specifications, blah blah blah, in use assuming the existence of those three. And then the hardest one to fix by far is hardware, because this is so freaking expensive to do and so complicated to make that like that's the reason there are
Yeah.
so few players doing that.
Yeah.
The example that came to my mind was the exploitation on one of the Intel CPUs. I already forgot which CPU was, but there was some scandal. Spectre, Spectre, something like that.
Oh, yeah, I remember that.
There was a scandal about Intel CPUs, which is this particular case, hardware security. Um, Each one of these layers must be addressed to some degree, blah blah blah. To judge how much effort must be put in making each layer secure, a threat model must be set up and a threat analysis done. Then a security policy must be defined, implemented, and verified. These activities are called security engineering. We're not going to talk about that. But we showed you how to make secure ADTs, and that's true. Um, these techniques are necessary for building secure applications on the internet, but are not sufficient. We also have to address the other layers for implementation security. We need a secure modular implementation. Building implementation secure systems is a research area with a long tradition. As an entry point, there is another language, which I was just
E
being
mentioned.
aware that there is an E language.
Oh, you didn't know about it. It's a
I
very
knew
nice.
A, B, C, and D, but I didn't know E.
Actually, E is unrelated to those. Funnily enough.
No, but all of them are kind of unrelated, right?
Uh,
Uh,
I mean, yeah, not kinda. I mean, D is named D because it's meant as a successor to C, and then C is named C
B.
because of B, and B is named B because it's a simplification of BCPL. And actually, has that name not because C comes after B in the alphabet, but because C comes after B in the name of BCPL, which is kind of funny, actually.
Yeah, but I didn't know E. Like, I didn't know E.
Yeah, E is actually unrelated to D, as far as I know. I think E is actually older, and it implements object capability security, which is very neat, actually.
Okay. And then finally, building applications. And then essentially, the rule of thumb is do it the dumb way first, and then we talk about it. So first, write the application without partitioning the computation between processes. Check with the correctness and termination properties of the application of one process. Most of the debugging is here. Second, place the threads on the right processes and give the object distributed semantics to satisfy the geographic constraints and the performance constraints. Yep. Um, blah blah blah. Yeah, all of this we already know. The application must be able to handle partial failure. Fault confinement has to be part of the initial application design. Yeah, this is something that it's very important and kind of understated in this paragraph. When we say that the fault tolerance needs to be taken into account when you go to a distributed setting, this means that you have to think that from the get-go. So you may actually have to make some choices that are not initially making sense in the context of the dumb version, but you're trying to future-proof yourself for when you do the second step. So this was the reason why CMO was initially done in Erlang, was because we already count that, okay, this is a game, and this is a game that inherently needs to be distributed in order to make sense. So we need it to be distributed later. We're gonna make it like local and centralized for now. What are we gonna do? And then we chose a technology, which was Erlang, because as an attempt to future-proof ourselves.
Yeah, because if you're on the beam, you have the flexibility of always adding more nodes later and sending some processes over there, right?
Yeah. It may be the case that if you pick some technology, if you choose some technologies without this mindset, when you go distributed, you're going to have a huge, expensive barrier to go through, rewriting everything in a technology that helps with that. Or you do a custom solution. Doing a custom solution requires some balls.
Or you
Because,
can go the dumb way and you just use microservices.
yeah, there is a trade-off between the communication mode and the fault-tolerant confinement mechanism compared to synchronous communication. Asynchronous, consider a system with three active objects there. T1 does an asynchronous send to T2 and continues assuming T2 is alive. Later, T1 sends a message to T3 under this assumption. But this assumption might have been wrong. T1 have been executing for a long time under this wrong assumption. So after it sends a message to T2, it did stuff and talks to people, assuming the liveliness of T2, but that was wrong. So you need to undo that. And if you are particularly in a mutable environment, you are done. If you are in an
Yeah,
immutable setting, there is still some hope, but if you are in a mutable one, you're just done. It's over. Um,
I have the high ground.
I have the high ground. With synchronous sends, this problem cannot occur because the synchronous sends blocks it. T1 does a synchronous send to T2 and it is informed that T2 has a problem before continuing. This confines the fault to an earlier point of the program. The trade-off between early fault detection and asynchronous communication is fundamental, like the choice between optimistic and pessimistic concurrency control. Which, by the way, have we read this already? I forgot.
Uh, we saw this way earlier when we were talking about locking and how to avoid deadlocks.
Oh, it's to preemptively try to get the lock before, right?
Yeah,
Mhm.
I kind of wish that the book went into more detail on lock-free programming because that's even more optimistic than what the book gives you, right? Which it presumes locking from the get-go. But yeah, we did see this.
With asynchronous communication, the application must be prepared to correct any false assumptions. There's different ways to realize fault confinement. One way is to build abstractions that do all the fault handling internally. If done well, this can hide completely the complexities of handling faults at a cost of having to use the particular abstraction. The global store mentioned before takes this approach. If you cannot hide the faults completely, the next best thing is to have narrow interfaces between them, between the processes. A final point is that a message passing programming style is preferable over a shared state style. Fault handling of distributed shared state is notoriously difficult. Yeah, so this
Yeah,
is essentially like, okay, maybe it's better to put a little bit of extra burden. Of course, you're gonna try to make the API of that very not very neat and very tight, but you're gonna have to handle. We have to interact with something else. There is another moving part. Um,
hello Ace.
yeah, hello.
Hello.
Distributed components. And so functors and resources are the key players in distributed component-based programming. A functor is stateless, so it can be transparently copied anywhere across the net and made persistent by picking it on a file. A functor is linked on a process by evaluating it there with the process resources that it needs. The result is a new resource which can be used as is or linked with more functors. Functors can be used as a core technology driving an open community of developers who contribute to a global pool of useful components. So this is essentially like, this was already true for functions, but functors are like also great, so why not do that with those?
Yeah, they are essentially module level functions,
Yeah,
so they are kind of neat.
yeah. And that's it for chapter 11. So we're gonna read chapter 12, and I think we settled on 2 sessions for that, right?
We did, yeah.
So we're gonna read all the way to where? Here or here?
Uh, that's a tough question.
I remember you saying that this was the the dance part of it, and maybe I'm wrong.
Um, I think Ace mentioned this as well, right? Last time.
About this book?
Well, yes, we were talking about it. Not the previous session, I think the one before that, if I recall correctly.
Well, I'll be honest. I haven't read this, but just looking at the titles of the subsections, yeah, it does look like that is the dense part.
Well, I was rereading this today actually, after I read the part for the book club just now. And I might be biased, but it didn't feel that dense to me. But then this is the second or third time I'm reading through this, so yeah, I'm not sure if that's correct actually.
Yeah, I mean, I'd be happy to revise that.
Um,
Um,
man, but okay, Benny, you read it today. You know that like we've been doing this book for like months, so you kind of know already the things that I pay attention to and the type of things that I ask. Can't you try to guess if I'm gonna also what's gonna be my feedback?
um, let's. Yeah, let's split this up like this. We do 12.1, 12.2, and 12.3 on one session, and then 12.4 and point 0.5 the other one.
Sure.
I
I'm gonna
think
stop
that's
the
sensible.
recording.